The National Electrical Code, or NEC, does not explicitly define voltage drop. However, it does define voltage regulation in Article 100. This definition states the change in voltage or current that accompanies a change in load, usually expressed as a percentage of the voltage or current change in relation to the initial value. Voltage drop is closely related to voltage regulation and is typically defined as the reduction in voltage that occurs along a circuit when an electrical load is applied. The NEC does not provide specific guidance on how voltage drop should be measured. However, industry practice is to measure voltage drop under load. This is because the load current will cause the voltage to drop due to the resistance of the conductors. Article 210.19 requires that circuits be designed to limit voltage drop to a practicable minimum, typically considered to be 3% or less. Article 310.15 B requires conductors to be sized to limit voltage drop to a value that will not cause unsatisfactory operation of equipment. Measuring voltage drop without a load will only indicate the source voltage, not the voltage drop that occurs when current is flowing through the circuit conductors and any connections. The amount of voltage drop in a circuit depends on several factors. Firstly, the length of the circuit. That is, the longer the circuit, the greater the voltage drop. Secondly, the conductor size. A smaller conductor will have a higher resistance and therefore more voltage drop. Thirdly, the amount of current flowing through the circuit. The higher the current, the greater the voltage drop. Fourthly, the conductor material. Conductors with higher resistivity such as aluminum will have greater voltage drop than copper for the same size. Voltage drop is a critical factor to consider in electrical system design and installation because excessive voltage drop can lead to several problems. Firstly, reduced equipment performance. Motors may not start properly or run at their rated speed. Lighting may be dim. Heating elements may not provide the correct amount of heat. Secondly, increased energy consumption. Equipment has to work harder to compensate for the lower voltage, leading to higher energy bills. Thirdly, equipment damage. Prolonged operation at reduced voltage can damage electrical equipment. Fourthly, safety hazards. Excessive voltage drop can cause overheating of conductors and connections, increasing the risk of fire. To accurately assess voltage drop, follow a systematic approach. Firstly, measure the voltage at the source. This is the starting point for comparison. Use a calibrated voltmeter to measure the voltage at the beginning of the circuit, typically at the circuit breaker or the service panel. Secondly, apply a load. Connect a load to the circuit that is representative of the expected usage. This could be a resistive load like a heater or a combination of loads. Ensure the load is sufficient to draw a reasonable amount of current. Thirdly, measure the voltage at the load. With the load energized, measure the voltage at the point of use. This should be done as close to the load as possible to include all relevant wiring and connections in the measurement. Fourthly, calculate the voltage drop. Subtract the voltage at the load from the voltage at the source. This difference is the voltage drop in the circuit. Fifthly, calculate the percentage voltage drop. Divide the voltage drop by the source voltage and multiply by 100 to express the voltage drop as a percentage. To remain within acceptable limits, the NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. However, lower voltage drop is always better for optimal performance and efficiency. Several factors can cause excessive voltage drop in electrical circuits. Firstly, undersized conductors. Using wires that are too small for the current they are carrying is a common cause. Secondly, long circuit runs. The longer the wire, the greater the resistance and voltage drop. Thirdly, loose or corroded connections. Poor connections increase resistance and voltage drop. Fourthly, overloaded circuits. Drawing too much current through a circuit can cause excessive voltage drop. To mitigate voltage drop, firstly, use appropriately sized conductors. Consult NEC tables to determine the correct wire size for the anticipated load and circuit length. Secondly, shorten circuit runs. When possible, reduce the length of the circuit to minimize resistance. Thirdly, ensure tight and clean connections. Properly tighten all connections and protect them from corrosion. Fourthly, balance the load. Distribute the load evenly across multiple circuits to prevent overloading. Conductor sizing is a critical aspect of electrical design that directly impacts voltage drop. The NEC provides tables and guidelines for selecting the appropriate conductor size based on the ampacity requirements and voltage drop considerations. Ampacity refers to the current carrying capacity of a conductor, which is the maximum amount of current a conductor can safely carry without exceeding its temperature rating. The NEC tables, such as Table 310.15, B16, list the ampacity of various conductor sizes based on their insulation type and installation conditions. When selecting a conductor size, it's essential to ensure that its ampacity is sufficient to handle the expected load current plus any applicable dirting factors. Dirting factors are adjustments made to the ampacity of a conductor to account for conditions that can reduce its ability to dissipate heat, such as high ambient temperatures or multiple conductors bundled together. In addition to ampacity, voltage drop is another critical factor to consider when sizing conductors. As previously mentioned, the NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop and determine the appropriate conductor size, you can use various formulas and online calculators. These tools typically take into account the circuit length, load current, conductor material, and conductor size. Firstly, determine the allowable voltage drop. Multiply the source voltage by the maximum allowable percentage voltage drop. For example, for a 120 volt circuit with a 3% voltage drop limit, the allowable voltage drop is 120 volts times 0.3, which equals 3.6 volts. Secondly, calculate the required conductor size. Use a voltage drop formula or calculator to determine the conductor size needed to keep the voltage drop within the allowable limit. The formula typically involves the circuit length, load current, conductor resistance per unit length, and a constant that depends on the conductor material and circuit configuration. Thirdly, select the appropriate conductor size. Choose the smallest conductor size that meets both the ampacity requirements and the voltage drop requirements. It's always better to err on the side of caution and select a larger conductor size if there's any uncertainty. Proper electrical connections are essential for maintaining a low resistance path for current flow and minimizing voltage drop. Poor connections can create hotspots, increase energy consumption, and even pose a fire hazard. Firstly, use appropriate connectors. Select connectors that are designed for the specific type and size of conductor being used. Ensure that the connectors are UL listed or otherwise approved for the intended application. Secondly, clean the conductors. Before making a connection, clean the conductors to remove any dirt, corrosion, or other contaminants. Use a wire brush or emery cloth to remove any oxidation from the conductor surface. Thirdly, tighten the connections. Use a torque screwdriver or wrench to tighten the connections to the manufacturer's specified torque. Over-tightening can damage the connector, while under-tightening can result in a loose connection. Fourthly, protect the connections. Protect the connections from moisture, corrosion, and physical damage. Use heat shrink tubing, electrical tape, or other protective materials to seal the connections. Fifthly, inspect the connections. Regularly inspect the connections for signs of corrosion, looseness, or overheating. Retighten or replace any connections that show signs of damage. Regular maintenance and inspection are essential for ensuring the long-term reliability and safety of electrical systems. Periodic inspections can help identify potential problems before they become major issues, such as loose connections, corroded wiring, or overloaded circuits. During an electrical inspection, it's important to check for the following. Firstly, loose connections. Tighten any loose connections to prevent overheating and voltage drop. Secondly, corroded wiring. Replace any corroded wiring to prevent shorts and fire hazard. Thirdly, overloaded circuits. Redistribute the load or add new circuits to prevent overloading. Fourthly, damaged components. Replace any damaged components such as circuit breakers, receptacles, or switches. Fifthly, proper grounding. Ensure that the grounding system is intact and functioning properly. Sixthly, GFCI protection. Verify that ground fault circuit interrupters or GFCIs are installed in areas where required, such as bathrooms and kitchens. Seventhly, arc fault protection. Verify that arc fault circuit interrupters or RSIs are installed in areas where required, such as bedrooms. Eighthly, smoke detectors. Test and maintain smoke detectors to ensure they are functioning properly. Ninthly, carbon monoxide detectors. Test and maintain carbon monoxide detectors to ensure they are functioning properly. Tenthly, proper labeling. Ensure that all circuits and panels are properly labeled for easy identification. By following these guidelines and consulting with a qualified electrician, you can minimize voltage drop, improve the performance and efficiency of your electrical system, and ensure the safety of your home or business.